Hi, in this video, I'll be talking about more topological properties of spaces, and this time we shall go through what are connected spaces. So connectedness is the opposite of like a separation. So what we define is we define a separation of X as a pair of open disjoint sets such that the union is X. And X is said to be connected if there does not exist a separation. And you can just think of it as your space is this. You are unable to split your space into U and V that are disjoint from one another and they cover the whole space. So it is a topological property and we'll see why later. And then we can also say that if A is a proper subset of X that is both open and closed, then it will form a separation. And so it is saying that if your space is connected, if and only if for all open U and V such that they are disjoint and union to X, then one of them must be empty. And it's trying to imply that the only open and closed sets in your topology is the empty or the whole set. That is what it's trying to say. So if X is just the singleton or empty, then it is connected. And so what it means to be connected is trying to generalize the singletonness of a set. So it's trying to say that the whole set is like one piece. So let's play around so that and show you more examples, then you can really understand this connectedness property better. So why do we say it's a topological property? Is because the image of a connected space under a continuous map. So continuous maps preserve the open set properties between each set. But now we can say that the image of a connected space is also connected. And we shall prove this because we can now suffice to consider the case of the surjective map first, because it doesn't really affect it. So let's suppose that Z is not connected, means you can find a separation. Then you can just take the pre-images of this separation, A and B, and they'll be disjoint in X, and the whole union is also X. And because their G is continuous, this will be open in X, and therefore they will form a separation of X, contradicting the assumption that X is connected. And so the image of a connected space must be connected. And so by saying it's a topological property, you're saying that if X and Y are homeomorphic, then X is connected if and only if Y is connected. An example of a not-connected space is you take the whole real line and you delete away 1.0, let's say. Then U can be minus infinity to 0 and V can be 0 to infinity. So this is not connected. Hence, R and R minus 0 are not homeomorphic. And the above example shows that a subspace, which is this, of a connected space R may not be connected. And so when can we say that a subspace is connected? It must be connected to by its subspace topology. Meaning you cannot find a separation in the subspace of topology of Y. Another way of saying it, and the proof I'll leave it to you to read, is saying that neither set A or B contains limit points of each other. Else you can find a neighborhood that intersects. Let's say A contains the limit point of B. Then you can find a larger set such that it forms a separation already. So when it's connected, a separation is one which neither of which contains limit point of each other. So when it's connected, you can always intersect them, and then this will become your new open set. But I'll leave it to you to read, then you better understand it, because this part is quite a easy to understand portion. Now we shall prove more properties about connected spaces, such that when if C and D form a separation of X, and Y is a connected subspace, then Y must lie entirely in C or D. And that's because if it doesn't lie entirely in C or D, then they will constitute a separation of Y. Because if C and D are both open, then C intersect Y and D intersect Y are open, and their sets are disjoint and their union is Y. So let's say this part is not then one of this part must be empty. And so if D intersect Y is empty and Y is a non-empty set, means D must be empty. And as a result, means that Y lies entirely in C. And so another property is that unions of connected spaces that have a point in common are connected. And the reason for that is because if not, we can find a separation. So usually when we want to prove things about connectedness, we assume that the space isn't connected first, because then we can make use of the property of a separation, of having a separation and leading to a contradiction. So I would say that if you practice more, you realize that you want to use proof by contradiction when you're dealing with connected spaces. So suppose that Y has a separation, then P being a point in common, P being one of the point can either lie in C or D. So P, let's say P is the element of C, and since A alpha is connected, it must lie within C or D. So it cannot lie in D because it contains a point P of C, and because C and D are disjoint, so it must lie entirely in one of these. So for all the alpha, it lies entirely in C, meaning the union of A alpha lies in C, and this contradicts the fact that D is empty, because it's just saying that Y equals to C, so D has to be empty. So it contradicts the fact that D is not empty, and we're done. Another thing to say is that any set that contains A and is contained in the closure, meaning in between A and this closure, will be connected. And that's also saying that the closure is connected. So suppose that there is a separation again, then A must lie entirely in C or D. So let's say A lies entirely in C, then A closure must be a subset of C closure. And since C closure and D are also disjoint, it means that B cannot intersect D. And this contradicts the fact that D is a non-empty subset of B. And you're done. So I hope that these properties are clear. Please go through again for you to better understand them. The last property we shall now show is one where it shows that a Cartesian product finitely is connected. And the reason for that is we are actually making use of the previous theorem where we proved that a union of connected subspaces having a point in common is connected. So we just need to choose a base point A cross B over here, then we just take the horizontal line here. This is connected because it's isomorphic to X. Then now we just take the vertical slice XY, and this is connected to isomorphic to Y. And then we just take the union of this, so it becomes this T, and this will be an open set that is connected. Now you form the union of all these T's. So it's like that, all the way. And then it must have a point in common, namely A cross B. Because that's where our starting point, our base point is. And so this union is connected. And thus, the union of X cross Y of this equals to X cross Y. And hence, X cross Y is connected. So if you get all the T's, then you get all the points in X cross Y. So the union equals to X cross Y. But because they have a point in common, A cross B, so the space is connected. And the proof for finitely many is just using induction. So you prove for one case, you can prove for all cases. And so you can see how connectedness is a really cool and important property of a topological space. And in the next video, we shall continue studying more about connected spaces, and namely we will now look into the real lines, because this is still a tutorial about real analysis. So I'll catch you in the next one. Bye.